first, I'm sorry. Okay, again, as I was talking about the lab, there will be no lab today unless you guys want to have a session on problem solving or finishing the lecture. It's going to be kind of a little bit of a heavy lecture, so we're going to get straight into it. Any questions first? Because we're done with chapter 21. We're going to go in chapter 22. And hopefully the recording will be available in time for those who are not in here. There will be discussion points in here, so hopefully you guys are going. Okay, from chapter 22, I already looked at some of the problems that we're going to be doing from this book. They're problem 55 for sure, okay? Problem 55, if you look at it from the book, it deals with data. And we do a lot of data in this class, okay? And actually in physics in general. So that's why I emphasize on them. So the fact that you're seeing me doing data, expect this kind of things also in exams too. So this is not something that is out of the realm of the possibility. So you need to be able to interpret data and analyze data and graph data, okay? I also will be doing it on Excel so that you guys can be more at ease with it, because I know it's something that you guys need. And also I'm going to do problem 52, problem 52, and problem 62, and problem 47. They're all identical in a sense. The geometry changes a little from a cylinder to a sphere to a non-uniform sphere, but the idea is the same, and I usually test on these things too. So you need to do, and this is calc-based stuff, okay? So you need to know how to get these things done, how to calculate the charge, how to calculate the electric field, and so on and so forth, okay? So that is basically I picked up already chapter problem 52, which is just between the two, but you could do either of these three problems. It's the same thing. I'm going to try, I don't know if we can do 53 or 54. They are similar to a problem you did in physics 4A when you were dealing with the moment of inertia, if you guys remember that. And basically where you have a blob of material and trying to determine its moment of inertia, for example, a disk, and inside the disk, there is a hole in it, okay? And you would want to determine the moment of inertia with respect to some axis. It doesn't matter which axis that is. And you would use the method called by subtraction. Basically, what you do in this case is you assume the entire disk is filled with the same density of material, and then you measure its moment of inertia, which is easy in this case for the case of the disk. It's 1/2 of mass times radius squared. And then you basically fill it with like a negative value for the other one, negative density for the other. It doesn't make sense physically, but it's a mathematical trick, okay? As if it's filled with a negative density, and then you solve for the density for the hole in it, and you find the moment of inertia basically as a difference of the two moment of inertia with respect to the center of mass. Once you find the center of mass and you find the moment of inertia, then you can find the moment of inertia anywhere using the, what is that called again? I forgot, the parallel axis theorem from physics 4A. Okay, anyway. Problem 53 and 54, they are similar in the sense that you have a charge distribution of throughout the shape. In one of them, in case is a sphere, the other one is a cylinder, and in some place there is a missing mass, it's hole in it. So you assume that it has a charge distribution of opposite sign, and you calculate the electric field due to one, and you calculate the electric field due to the other one using the different sign. And you take the difference between the two, and now you have found the electric field everywhere in the shape, okay? Whatever you're asked to do it anyway. Use superposition principle for that. So that's problem 53 or 54. And now if we can get to them in this exam, we will get to them in some other exam, later exam, because there will be actually a similar approach to when we do the magnetic field, because today we'll be exploring Gauss's law. When we do the magnetic field, we're going to be exploring Ampere's law, which deals with currents creating magnetic fields. And in that situation, again, the same method will appear again. So whether you use it in the moment of inertia or the center of mass way back when you were doing physics 4A, or now in this chapter, we're doing Gauss's law for the electric field, or down the road when we do Ampere's law for the magnetic field. Do you guys remember this thing or not? Does anybody remember what you guys did? At least when I teach that class, I used to do it. I know. I don't know why you guys did or not.
It sounds familiar.
Yeah, okay. So that's basically how the idea behind it too. I'm not saying we're going to do problems 53 or 54, but I'm hoping to at least get some time to do them. Okay. Here is the deal with these 3 chapters so far. Chapter 21, 22, and 23. All these 3 chapters, let me put this book, it's a heavy book, man. All these 3 chapters, they deal with one thing, and that is the electric field. Okay, let me share with you the screen in here to see exactly what we're talking about. Share. You guys looking at the OneNote?
Yes.
Yes.
Okay, so these 3 chapters deal with the electric field. The first one was basically a brute force, chapter 21. Just do the integral, okay? 1/4πε0, the charge divided by distance squared, then the r hat, and integrate that. If you can, that is actually one way of doing business. Sometimes it's too tedious and too long, and it may be complicated, so you'd rather do another method. And that is what chapter 22 comes into play. Chapter 22 gives you an alternative approach to it. Okay, it looks uglier actually than the first one, because the first one has actually an integral over the charge distribution, which is a volume. This one will have actually 2 integrals in it. Okay, instead of you have still the charge on one side. On the other side, you'll have a double integral over a surface. So that's what Gauss's law is. But the promise of Gauss's law is it takes advantage of the symmetry so that you do none of the above, or if you do, you do the least amount of integration possible. So that's really the advantage of Gauss's law. Gauss's law is useful in the case of symmetry. If it's not symmetry, you have the same level of difficulty, if not more, than chapter 21. So it takes advantage of symmetry to help you solve the problem. So that's really what chapter 22 is. Chapter 23, because look, chapter 21, basically, you have to integrate you're going to get the r hat in the numerator, which is a vector really. It has components in the x direction, it has components in the y direction, it has components in the z direction. And this whole thing also depends on the coordinates x, y, and z. So you have a function or 3 functions, ex, ey, and ez, that depend on x, y, and z in space. And this is the case of electrostatics. In the case of electrodynamics, when time comes into play, these functions, they depend also on the time t. So it's a very complicated stuff most of the time. So instead of that, chapter 23 comes into the play to reduce the difficulty a little and introduces the concept of the so-called electrical potential. Electrical potential is a number. It's a scalar function, and a scalar function has only 1 function instead of 3. It still depends on x, y, and z, and potentially t too, but I'd rather have one of them, one monster, if you wish, to work with, than 3 of them. Okay, and that one, there is a relationship between the electric field and the electrical potential. At the end, once you find the electrical potential, you should be able to go back and find the electric field. So the whole deal is about the electric field, trying to find it really, because if I find the electric field, I can find the force, which is the charge times the electric field. And if I find the force, I'm going to go back to F equals to ma. Do you guys understand the plan of action? The first thing that you're supposed to do is find E. Chapter 21, integrate. Go back into the definition and do your thing. It's a vector. It has 3 components that depends on space variables in general. This stuff is hard, okay? Sometimes that's the only way to go, okay? This chapter 22 uses Gauss's theorem, and that actually reduces the problem using symmetry. So if the problem has symmetry in it, the problem is kind of easy. using Gauss's law. It's still the hunt for E. And then chapter 23, if these two fail, you're going to integrate here a vector. You're going to do the same thing, but for a scalar. And a scalar has less components than a vector, that's all. So that's the 3 chapters for you. It's still finding E. Once you find E, you're supposed to go and write F equals to QE. And now since you know the force, you're going to equate this to MA, and you're back happily in where you're supposed to be, where you're chapter 4 from the book, okay? As I said before, excuse me, I'm going to not talk too much about this one in here because I'm assuming that down the road we'll be doing it anyway. And it's going to be repetitive and a kind of old-fashioned, so we're going to skip that thing in here because we know what we have in mind. So the thing is, try to find the force in here, okay? So here is the deal where we are right now. I'm going to take a point charge. So this is a point charge Q. I'm going to assume it's positive because if it's not positive, things will flip, that's all. I'm going to go a distance away from it and find this electric field. For a point charge, remember, it's 1 over 4 pi epsilon naught times the charge divided by the distance squared. So I can compute this number. I will find it exactly how much it is. If I know this distance, if I know Q, and I have 1 over 4 pi epsilon naught to be 9 times 10 to the power 9, I can find that vector, and it's radial. It's pointing away from the charge because I assume it to be a positive. If I move away distance in here, I'm going to calculate it, but because clearly this distance is a lot less than this distance, this vector would be a lot bigger than this one. So here is, I'm going to represent this vector. Do you guys understand? If I move further away to this point in space, the vector probably would look like this. You guys see what's happening now, don't you?
Yes.
Yeah, it makes sense.
Yeah, if I go on a sphere now, you have to be careful now. I'm on a sphere, not a circle, because sometimes we get confused between this shape and the actual thing. This is a sphere, not a circle, okay? And go to any point on that sphere, it's going to be the same thing because the sphere has the same radius. So the number is going to be the same, regardless of how I'm going to write it, okay? The pointing, though, is radial, is pointing away still. But how big the vector is, it does not change on a sphere, as long as I am on the same sphere. You guys understand? Yes?
Yes.
Here's the thing. If I go on this sphere, though, I'm going to find the same thing as before, except that now the length of this vector is going to be the same as this one, not as much as the other one, and so on and so forth, okay? I know more about this electric field if I draw it that way. But there is a trouble in here. Do you guys see that? Let me explain what this problem is. This is not the only field that I have between this point and this point. There is another one between them. Do you guys see that? There is another point at least that exists between these 2 points. You see it? Somewhere in the middle. So there is this point where the electric field now, if I calculate it, is going to be less than this one, but more than that one. Yes?
Yes.
Yes.
Yeah.
Here's the trouble. This is not never-ending story. Between this point and this point, there is another point actually too, in the middle too, which is longer than this one, but shorter than that one. So it's going to be somewhere like this. I'm going to try to do my best to meet that requirement. And between this one and that one, there is another point. As a matter of fact, between any point and point, there is another point in here where actually this one will be the longest of this bunch in here. And this one will be slightly bigger than this one, but less than that one. And so on until the whole thing. Let's just this line. I have to do this on this line too. I have to do this on this line too. I have to do this on this line too. Guess what? I have to do it also in between too, because there is between these 2 points, there is another point in here. And I have to do the same thing in here. And between these points in here, you guys see that it's going to be messy and ugly very quickly for representing the electric field. You think I'm going to end?
No.
I think it's just going to keep going.
Yeah, till infinity.
To infinity. At least this is not an infinity of a regular kind. This is an infinity that is complicated because on a single line, it's an infinite amount of lines, points. And there is an infinities in here. So this is a different kind of infinity in here. So technically, we're never going to be done with this. So we need a way of representing the electric field that solves these problems. So here is the deal. Instead of having to draw all of these lines like this is what I'm going to do. I'm going to come back in here and say, here is still my charge in here, Q, and I'm going to draw a line. Because this line tells me that there is an electric field in every single point in here. And just give it an arrow, because this is positive. I'm assuming it's positive. If it's negative, by the way, the whole picture reverses, that's all. All of these vectors keep their magnitude, but all of these things is pointing this way, that's all. Because the electric field for them will be pointing inside. So this is the negative charge, but this is now the other positive. So that's the picture will just be slightly different, and that's the end of it. Now, this is how am I going to draw this electric field? Now I'm going to draw lines. Because I know between each and every one of these points, there is a point. So no matter how good I do, I just draw a whole line at the end of it, okay? So this gives me more detail than the previous picture, because this one was lacking the fact that this electric field is defined everywhere in space. This one tells me that. Do you guys see it? Now it's defined everywhere, okay? At least on this line. Good?
Good.
Are we good with this?
Mm-hmm.
Here is the trouble, though. We lost another piece of detail. In here, when I draw the vector basically for the electric field, I was very careful to state if I am closer, the vector is longer. If I am further away, the vector is smaller. So I was really, in this representation, I have a sense of how strong the electric field in here. This one is less than that one. Do you guys see that? This picture doesn't show that. We lost that detail. We don't know how strong the electric field now is, at least, because it's just a straight line. You guys see that we lost a detail in the process?
Yes.
And it's a big deal, so we need to recover that. If we somehow recover that, we're in business. That's the only thing that, then this picture will be good. So this is what we're gonna say. We're gonna agree from now on to draw a certain number of field lines. These are called field lines, by the way. Because here is the thing. Let me show you what this is going to happen. If I double the charge in here, it says, for example, I have 1 Coulomb, now I have 2 coulombs instead. This line will be longer, and this will be twice as long. All of these lines will be there, and we have no problem. But if I double the charge in here, it's a line. How are we going to make an infinite line longer than infinite? It's infinite already. If you double an infinity, it's still infinite. You guys understand? So that's why this detail is valuable in this representation and is lost in here. You see that? That's why this detail is important in the field line representation, where it's just a certain line extending to infinity is lost. If I double the charge in here, it stays the same thing. The line stays the line. There is no problem with it. It doesn't change. So what I'm going to say in this case is the following. If you double the charge, just draw more lines. That's all. So draw. If you double the charge, instead of drawing 4, draw 8. Now I can see I have more charge for this one because I have more field lines. Do you guys understand?
Yes.
Yes? So to measure now the length, the strength of this field, I'm going to use this trick. I'm going to use something called the field density, the density of the field lines. Because it looks like there are a bunch of them now, then they are in the situation where there's only one charge, okay? So what I do with the density is I count how many of them that cross an area of a square meter. So if this is 1 square meter, 1 meter squared, I can count there is 1, there is 2, there is 3. But if the charge is only 1 Coulomb, I'm going to get less. I'm going to go back into 1 Coulomb picture. So this is 1, we agree to draw only 4 per Coulomb. And since this is 1 Coulomb, let's charge. And if I draw the same 1 square meter in here, I'm going to see that there is only one line that crosses that square meter. So if I agree to measure the density of the field lines, I am in business. I have recovered the strength of the field. If you double the charge, there will be more field lines. If you triple the charge, there will be more, 3 times as many. If you take it by half, there will be 1/2 of the original field lines, okay? You guys see the point in here?
Yes.
So keeping that in mind, that you draw infinite lines and draw as many needed per unit charge. So if you agree to draw only 4 per unit charge, then if the charge double, make sure you double the number of field lines. If the charge is 1/10 of what was originally, draw 1/10 of it. Obviously, 4 lines is not going to cut it for 1/10 of a charge. So probably I need to draw 1,000,000. Okay. If 1 Coulomb, draw 1,000,000. Then 1/10, draw 100,000 when it's 1/10 of a Coulomb. Do you guys see that? Just basically as simple as that. Or you know what? There is a better number that I can draw, which is 1/epsilon naught, which is of the order of 10 to the power 9, which is actually 1,000,000,000. I mean, obviously, I'm not going to be sitting in here and drawing billion lines. Hopefully, you guys don't expect me to do that, because we're going to be here forever. But if we do that, then that is it. So if you draw, for example, this is if it's 1 Coulomb. If it's 2 Coulombs, draw too many as much as this one. If it's Q Coulombs charge, whatever Q is, for example, 10 to the -6, it's fine. Draw 1,000,000th of a billion, which is still 1,000 lines. It's a huge number, okay? So Q/epsilon naught, this is basically the number that we're going to draw for Q, because we agree to draw about 1/epsilon naught per line, per Coulomb, I'm sorry. So if it's Q, just multiply that number by Q and end of the story. So this will be my density of field lines. Actually, the number of fields, the number of lines, actually, the number of lines in this case. Sorry, the number of lines to draw, period, end of story. The density has to do with the area. The density, you need to bring an area in here and count how many lines will cross. Obviously, if Q is less, you will have less lines that cross it. But if Q is big, there will be more lines in here to cross it. And now we're in business. We are representing the electric field with these so-called field lines. So let me give you a couple of representations for the stuff that we saw right now, and we will go through it later on, okay, and how to tackle this one again. Let me go first of all for a negative charge, negative Q and positive Q. We saw this one. This is the dipole, by the way, okay? If I go with the original representation and calculate the electric field in here, that's where we calculated. We found this line. If I move away, I expect this line to be less and less and less, so on and so forth. And in here, it's going to be actually closer, because remember, it's 1/distance cubed when you're far away. So as you get closer, it's going to be higher and higher. And of course, the dipole approximator doesn't work, so you have to use the correct expression, but that's going to be this line, okay? On this side, actually, if I calculate it, it's going to be this line. And it's going to be coming into the negative charge in here. So it's emanating from the positive charge. And in here, if I do the calculation, it's going to come out here. And in here, it's going to go like this, straight out. And in here, it's going to go in here. And this picture is symmetrical. Whatever happened this is what we calculated also. The electric field right smack in the middle. It was pointing this way. Okay, so this we calculated it already. And this now is the so-called field line. The electric field is actually tangent to this field line, always. Okay, in this case, it's the same line, but in here, it's going to follow this curve and come back to it. So this is how the electric field looks like for a dipole. Okay, so this is the source of the field lines. This is like the faucet. Oh, man. And this is the sink for the charges. So the negative charge is always where the field lines will go and end. The positive charges where the field lines will emanate from it, will come from it. So if I have, for example, only two sources, then I have a problem. I have to represent that correctly. So let's say, for example, I have a positive charge and a positive charge. And this one is pushing field lines. First of all, there's no problem with it pushing it this way. This one has no problem pushing it with it. Both of them are positive. This one will try to push a field line to this one, and this one is pushing a field line. So when they come in here, they actually will not meet. They will all go to infinity. Same thing in here. And the same thing in here. Obviously, the field lines in here, they look this way. So does this make sense to you guys, the picture? If the charges are positive? Yes?
Yeah, that makes sense.
Yeah.
If they're negative, it's the same arrow, same lines, except that they're pointing toward the charges, that's all. What if I double this charge, for example? Then in this case, this charge will try to push the field lines as close as possible. Let me draw it. As close as possible, but then when you get close, the field becomes stronger for this one. So it's because, remember, one of distance squared. So this one will repel them. So yes, it's going to shift toward this one because this one can push further, but it cannot push it all the way in. So this is for when this charge is twice as many as this one, and so on and so forth. So this is the representation of the electric field. And
Professor,
here I have two
question.
sources, though. I'm sorry?
I have a question. How does that work when you go towards a black hole?
Oh, okay. First of all, those are not charged particles. They're gravitational fields. We'll discuss that some other time, okay?
Fair enough.
Okay, so I know that these are actually, if you look at them from a different perspective, they're called the Coulomb Mounts, because there's a mountain in here, actually. A hill. And there is actually another hill in here. Both of them are hills. But in the case of the dipole, this is a hill, and this is a, we're going to get in the electrical potential later on, and you will see exactly what I mean by this electrical mounts. This is basically Coulomb's mount, okay? So that's because of the fact that the positive charge is sitting in here, and the negative charge is sitting in here. So basically, we're going to talk about this. In other words, if you drop a positive charge in here and you would want it to come closer, it's not going to get close because it's going to find the potential that is so high it cannot climb near a positive charge. But it's going to find the negative charge in here is going to go straight to it. That's why it's a climb, basically, for the positive charges near the positive charge, and actually downhill for near the negative charge. Anyway, so this is the representation of the electric field, and this is the source, and this is the sink for it. Because of this analogy with fluid dynamics, we're going to borrow those ideas from fluid dynamics and try to apply them in this case, and try to find a way of measuring how many field lines are coming from a given charge, okay? So let's do that. In fluid dynamics, this is like stream, for example, okay? All of a sudden, I'm using blue now. Let's use this color instead. So we have a stream in here, okay? And I want to capture how much volume of flow in the stream is. How much? So this is water now, or whatever you want to a fluid, okay? This is hydrodynamics, flow in a fluid, okay? So I want to know how much. So I'm going to come into this. I'm going to take this simple shape in here for the flow. So this is an area A. And I want to measure the volume of the fluid that passes it per second. So what I do in here in this case is I wait a certain delta t amount, and this fluid is moving with constant velocity v, by the way, uniform. The same velocity, that means what uniform means, v is constant, okay? So if that's the case, after delta t amount of time, there is this much fluid passes by, delta x. You guys see that? In delta t. So the volume is clearly, what is the volume of the fluid that passes by? How much is it going to be? What is the volume of this fluid that passed by?
Is that just x cubed?
The area is A, and the displacement is delta x. I have the heights and I have the area. Area. So what is this volume here? So basically, this is the shape that I'm trying to find its volume. So the area is A. Let's call this one L, and let's call this one W. The width is W, and the area, the height is L. And it moved after delta T amount, this distance delta X. So I'm curious, trying to find this volume in here. How big is this volume? So this is W, this is L. What is the volume now?
Would it just be LW times delta X?
Does everybody agree?
Yes.
Yeah, just the area times delta X, that's it, okay? Because it's just simple, just rectangular, what is it, shape, the rectanguloid or whatever. Basically a shape that is just the area times so that's the volume, okay, V. The rate at which the fluid flows is what I call flux. So by definition, the flux phi, flux is, by definition, is the rate at which this fluid is flowing per unit time. Obviously, LW is just the area A, okay? And what is delta X over delta T? What is delta X over delta T? What do you guys think? Isn't it this the velocity of the fluid? Because
Yes.
if I measure delta X per unit time, that's the AV. So this is the flux, the rate at which the fluid is flowing. So that's basically what I mean by the flux in this case in hydrodynamics. So let's take this analogy more. Let me redraw the shape in here a little bit with the, so again, there is a tube of some sort that is a rectangular shape, which is probably not practical, but this is a mathematical construct so that we don't have to worry about the shape of the area. It's much easier to do it, to draw a rectangle for the area. So this length is L, this length is W. Here's what I'm going to do. I'm going to take another area though. I'm going to take this area. So this area was A, by the way. The original area was A. A is equal to LW, okay? And I measured the flux then, if you guys remember, is equal to AV, where A is just the area times the velocity V, okay? So I'm going to change a different area now, and I'm going to show you how this area looks like. It's the same width, except it's tilted a little. I'm assuming that there is a line in here that extends to infinity here. So this is the same area. Would you say, if there is no sink in here, if there is no puncture in this conduit, there is no hole where there is actually the water is dripping in here, or there is no pump in here, there is no source in here pumping fluid, that the amount of fluid that passes in here per unit set time is the same fluid that passes in here or not?
Given that the new sheet, it looks like from this L side, it's got a right triangle, I'd say that it's slightly bigger area.
Okay, the area is bigger, you're right. Okay, I know. But the flow in here, the water, the amount of water that passes this area, A, I'm going to call this second area A prime, by the way. The water that passed A would be different or the same amount of water that passes through A prime. Granted, there is no sink, there is no hole in here, and there is no source in here. This is a sealed conduit.
It would be the same.
Does everybody agree with Justin? Yes?
Yeah.
Yes.
Yeah, absolutely. So there is no reason for it. So the flux in this case, which is AV, must be the same flux that passes through A prime. So I need to find the same flux, which doesn't change in here, a constant rate, by the way. I explained that before, in terms of the new area, that's all. That's really what the challenge is. I'm gonna go back into the second area now and draw the shape a little bit differently, okay? I'm gonna come right through at the edge and look at the area. Here is how the area look like. The area A looks like a line. I'm looking at it in here. So I come in here and look at this whole thing from this angle. So this is the way I'm looking at things. So this is the area. The width, I cannot see it because it's going into the screen. So this is L. Do you guys see that? And they both have the same width. I made sure of that, okay? Both have the same width, W. So the second area has the same width, but as I think Justin or somebody has mentioned, is slightly tilted. So in this case, its length is not L, but rather L prime. So the new area now is clearly A prime is L prime W. Do you guys agree with me?
Yes.
Yeah, it's longer length. The width is the same, but the longer length. So if I take this and flatten it and look at it, now it's actually this is how it looks like. So basically I'm looking at it from that angle, from that side. Now, the vector, the velocity V in both cases was this way. So from this area, this is where V is. Okay. I want to ask you about this angle in here. This is the angle of the tilt, theta. The area is actually a directed quantity. The area is actually a vector, not a scalar. Okay, I don't know if you have seen that yet in calculus or in vector calculus more specifically. But the area, if I tell you, for example, this is 8.5 by 11. So what is the area of 8.5 by 11? It's exactly 8.5 times 11. Okay. So so many in square inches. Okay. So now you take this one and you turn it around. If I give you the area only, you don't know which way the area is pointing. It could be pointing this way, it could be pointing this way, it could be pointing this way, it could be pointing whichever way that you can think of. So it has a magnitude. It's like you give me the speed. You tell me I'm doing 50 miles per hour, but you don't tell me which direction you're traveling. It's the same problem. Same thing. If I tell you the area in this case is so many square inches, and I don't tell you which way is pointing, then you have no idea which way is going to be pointing. So it's a vector quantity. It's not the volume, no, the volume is a scalar. If I tell you this is how many cubic meters, there is no way to tilt it. It's always the same number inside, okay? So the volume is a scalar, the area is a vector. And the direction of the area is actually given by the right-hand rule. Length crossed with width, and then is going to be pointing and given by the right-hand rule. So as a matter of fact, in this scenario, the first area was pointing this way. So A has this direction. So this is A. And now, if I use the same rationale, the right-hand rule makes it so that it's perpendicular to both L prime and also W. And it's going to be the perpendicular to W anyway if I draw it on the screen, just like A. But it needs to be also be perpendicular to L prime. So this is actually where A prime is. Okay, it's a vector. And so is V, actually, by the way, it's a vector. What is this angle between the area A prime and V? You guys, can you tell what that angle might be in terms of theta?
It would be the same theta.
Can you guess why? Can you tell me why? Does everybody, first of all, everybody agree with Justin, or he's talking nonsense again?
I think I agree because it's V is perpendicular with A, and
Perpendicular with this
So-
side, you mean? Hold on.
yeah,
Let me, not perpendicular with A, it's perpendicular, you mean with this side. So this side and this side are perpendicular, yes?
yes,
And you're saying that this side of this angle is perpendicular to this side of the other angle theta.
Yeah, that's why they would have angle theta.
Yeah, that's
between
correct.
as well.
That's the reason for it. Where there is a theorem in geometry a long time ago that you guys saw that basically state that if two angles are they have their sides mutually perpendicular, they must be the same. Okay, so apparently Justin is right too. Okay, so Drake has confirmed it basically there. Does everybody agree now that these two angles are the same? This is actually theta too. Well, if you still have any doubts, let me give you another piece of mind in here to clear that out for you. Okay. Okay. Let me explain this from a simpler approach. I mean, that's correct. There's a theorem in geometry that says that, and Drake is 100% correct, and so is Justin, by the way. So this is V. This is the area A prime. Okay. I know this angle is theta. If I extend V to this direction, of course, it's perpendicular, as Drake has mentioned. So this angle is 90 degrees. And this angle also is 90 degrees because this is the definition of the cross product. So this is a 90-degree angle, and this is a 90-degree angle. The sum of this angle with this one is 90 degrees because that's inside a triangle. So theta plus this guy is 90 degrees. And this guy plus this angle also is 90 degrees because this is 180 degrees, take away 90. So you're left with this two adding up to exactly 100 and I think exactly to 90 degrees. So this complements this one, and this one complements theta. So therefore, this must be theta. Does this make sense now?
Yes.
Yeah. Okay. So if you're convince yourself that's theta, okay? Because it is, okay? One way or the other, use the theorem from geometry or use this approach to argue that actually the two angles are the same. So this angle between A prime and V is the same thing as the angle with which we tilted the surface a little by the angle of theta, okay? So, and by the way, how L and L prime are related, it's very simple from this geometry. L prime is the hypotenuse in this big right angle triangle, and L is adjacent to the angle theta. So I know from this geometry of L over L prime is simply cosine of theta. So I know exactly that L prime is going to be L over cosine of theta. So in other words, this is actually L over cosine of theta times W, which is A over cosine of theta. So we know how these things are related to one another. And as somebody else earlier mentioned, this area A prime is bigger by actually 1 over cosine theta because cosine theta cannot be greater than 1. It's between 0 and 1. So at best, it's going to be equal to A. If theta is 0, cosine of 0 is 1. But if theta anything more than 0, cosine of theta is less than 1, and A prime, you're dividing by something less than 1. So A prime is definitely bigger than A. Okay, so that confirms the argument that was made earlier, except my point then was the flux must be the same through the area A and the area A prime, okay? Having said that, this is how the flux looks like now. The flux is equal to the area A, and the area A from this algebra is clearly A prime times cosine theta. A is A prime times cosine theta. So from this argument in here, so this is actually A prime cosine theta times V. So that's what this expression is. So let me rewrite this one and leave the cosine theta by itself. So the flux phi then is equal to the area A prime times V times cosine theta. From this shape, clearly, theta is the angle between A prime and V. Does this ring a bell with you when you see a vector magnitude times another vector magnitude times the cosine of the angle between them, because theta is the angle between these two vectors, A prime and V? What is this operation called? Do you guys remember what this is? The magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So you did vectors in physics 4a, didn't you? Yes?
Yeah. Although it's sadly been a while, so I'm kind of jogging my memory with this stuff.
This is the dot product. Does this ring a bell now? So this is the dot
Okay. Yeah.
A times V. That's all. So when you do A times V, you take the magnitude of A, in this case A prime, I'm sorry, and times V times the cosine of the angle between them. So this is the dot product. Yes, which is a scalar, which is a number. When you dot two things, a vector and a vector, it becomes a number. It becomes just like a number 12 or 13 or 27 or whatever number you can think of. Does this ring a bell now to everybody else, the dot product from Physics 4a?
Yeah, it looks familiar.
Okay.
Yep.
Okay, so this is the flux then in this case. The only reason why it was AV to begin with in the case of the area is because the angle was 0. For the area A, the vector V and the area A in the same direction, so theta was 0. That's why we ended up with AV. But in the area A prime, since I tilted it, the flux turned out to have the cosine of theta, which is the dot product. As a matter of fact, if you tilt this area so much, like this, the flux is going to be 0 because the angle will be 90 degrees and cosine of 90 degrees is 0. And you ask yourself, how much flow of water on a surface that is tangent to there is no hole in here, so there is no water that is going to come out. All the water is going this way, so the flux better be 0 in here. You guys see that? Makes sense, doesn't it? Because the area is pointing this way and the velocity is this way. This is the new area, A prime. So cosine of 90 degrees is going to be 0. So if I do the dot product of these two vectors, I'm going to end up with 0. Does it make sense now with the hydrodynamics?
Yeah.
So we're going to borrow that idea from hydrodynamics and define our electrical flux. So similarly, we're going to define the electric flux. By definition, the electric flux is going to be equal to now here is the trouble. If E is constant, if V is constant, then just do that, you're right. But if V is not constant and the flow is on some sort of an arbitrary shape in here, okay, and the area itself is arbitrary, it could be actually twisted. So you really have to take an element of an area in here. This is the area A, dA actually. And the flow in that case is V, and V may change with the area. So in this case, the flux in hydrodynamics also is equal to the integral over the area itself of V dA. So that's how the flux is defined in hydrodynamics. We're going to follow the same step in here and define it as this double integral. And as I said before, the promise is that so that you don't do it. Okay. Or when you do it, it's going to be very trivial. So the same thing, we're going to define it as E dA over a surface, in this case, an arbitrary surface. Okay, just basically that is the flux of the electric field over that surface. And actually what it measures the number of field lines that pass through it. Okay, it's that same thing that I was talking about earlier when we said that bring that square meter now and find how many field lines that pass through it. That is actually the interpretation of this flux. And we're going to find it, okay? We're going to find this value, okay? So this is by definition of the flux. If you're curious trying to find the units for it, the units for the electric flux, and that's why we put the letter E in here, to distinguish it from hydrodynamics, and also because there is another flux that we're going to see down the road, the magnetic flux. And the magnetic flux was famous enough to have its own units, actually. It's more powerful than this flux. The units for this guy are just the units for the electric field, which is a Newton per Coulomb, times the units of the area, which is meter squared. Okay, the units for the magnetic flux, which is phi b, at that point is going to have a unit. It actually has the Weber, okay? For this one, we're just going to use Newton per Coulomb per times meter squared, okay? So that's the units for it. So in a case, for example, let me give you an example in here. Let's say, for example, this shape, cube. Not, yeah, a cube, it doesn't matter. It doesn't have to necessarily have the same sides, it doesn't matter, okay? And go in a region of space where the electric field is constant. And for simplicity's case, I'm going to take it to be in the x direction, okay? It can be any direction you like. So it's going to come, a field line comes in here and penetrates through the surface and comes out from here. And another field line comes in here and penetrates and comes out from the other side, and so on and so forth. So there are so many field lines that are all in the same direction. So if you're curious trying to find the electric flux in this situation, in this area, the electric field is pointing this way and the area is pointing this way. So the angle between them is 90 degrees. And I know that there is no flux because, again, it's the dot product of the area times the electric field. So the flux on this side is 0. I'm going to call this area 1. Is equal to 0. And the flux of this, the other side, the electric field is pointing this way and the area is pointing down. So the flux also is 0 on area 2. So these two sides will have no flux because, again, the electric field and the area are perpendicular to one another. On this side now, facing me, the same thing. The area is coming in here and the electric field is on the x-axis, so there is no flux in here either. On the other side, opposite to the other one, again, the same thing, but except that the angle is actually negative 90 degrees, it's still 0. Cosine of negative 90 degrees is still 0. It's this area now where there is a flux. Because in here, the area is this much, and the electric field is this much, and they are both parallel. So let's say, for example, I have 10 Newton per Coulomb, and the area is 1 square meter. So this is clearly 10 Newton per Coulomb per meter square, okay? There are some homework problems that you can do this calculation in here. And on this side, though, the area is actually pointing this way, and the field is pointing this way. So if this is 10 Newton per meter per Coulomb, and the area is still 1 square meter, but I'm sorry, the electric field is pointing still in the same direction. Why did I put it in the wrong direction? The electric field everywhere is pointing in the same direction. So the angle between them is 180 degrees. That's the bottom line. So this is actually, the flux is going to be negative 10 Newton per Coulomb meter squared. So what is the net flux now? What would be the net flux for this entire cube?
For the cube, it would be 0.
Yeah, because add up all of the other numbers and it's going to be exactly 0, okay? So in this case, it's easy enough to calculate because the electric field is uniform. In general, it's not uniform though, and you really have to do some honest work if you're curious trying to find the flux. But again, it's a means for something, that's all. It's not really an end by itself. As a matter of fact, it's not famous enough even for people to care to give it units, okay? So it's just, this is how the definition of the electric flux is. And as I was saying earlier, it's really the measurement of those density of field lines. How many field lines go through, okay? That's all. The more there is, the more flux there is. Okay. Let's calculate the flux of a point charge. Flux of a point charge on a closed surface. So this is one type of calculation that we need, which is the surface, not just any surface. This surface better be closed. As a matter of fact, initially I'm going to take it sphere, which is a special case of a closed surface. So we're in the special of the special. So we have now a charge, Q, and we have a sphere, not a circle, okay? This is a sphere. Just to make sure you guys understand, I cannot draw a sphere on a two-dimensional surface. Now I want to find the flux of the electric field on that surface. So let's see what happened here. First of all, the area is radial. dA is radial. The electric field actually is also radial. As a matter of fact, I know its value. Its value is equal to 1 over 4 pi epsilon naught times Q over R squared times R hat, which is the radius in this case, okay? So the dot product of an R hat and an R hat will give me exactly 1, because this is a unit vector. So if I dot r hat with itself is going to be the length of a unit vector is 1. The length of the second unit vector is 1 times cosine of the angle between the same vector, which is 0 always. And cosine of 0 is 1, so this is 1. Okay, the dot product of a unit vector by itself is always 1. Okay, the dot product of a unit vector r hat, for example, with any azimuthal angle with the direction that is perpendicular to it is going to be 0, because this is perpendicular to this one. So cosine of 90 degrees is going to be 0. Because this one, although this one has a length 1 and that one has a length 1, but their dot product is going to be 0. This is just a refresher from you guys, what you did somewhere in physics 4a. So the flux then, the element of flux on this surface. This is a patch on the surface, not the whole surface, okay? So on a patch, on a sphere, then the electric flux, the element of the flux, is just going to be EdA, because cosine of 0 degrees is just 1, because both of them are parallel vectors now. dA and E are in the same direction. Okay, so that calculation in here, this dot product becomes just the product of the two quantities, which is easy. Furthermore, when I'm summing through a sphere, the electric field is the same. As a matter of fact, the electric field on this sphere is the same value, because it depends only on 1 over r squared. Since r on the sphere doesn't change by definition of what the sphere is, then E is constant. So all I'm left with then is the flux on the electric field for the entire sphere, which is 1 over 4 pi epsilon naught times q over r squared times the integral of dA over this closed surface. When you see the circle in here, that means it's a closed surface. As a matter of fact, I know what the surface in this case is. It's a sphere. So that is a representation of the integrals when you're doing multivariable integrals. Any one of you guys did more than Calc 2? I mean, did you guys get into this stuff with multivariable functions or not yet?
You know, Calc 1C?
Yeah, it really doesn't matter, because we're not really going to do a double integral or triple integrals whatsoever. But the point is, this is the definition. Okay, so now the summation of dA over anything is going to be A. So what I want is the area of a sphere. So that's basically what needs to go in here. What is the area of a sphere whose radius is r? You guys know from your previous classes, from geometry? You can Google it if you like.
I think
What
it's
is
like
the area of a sphere?
4/3 pi r cubed.
That would be the volume. If you take the derivative of that, what is that supposed to give you? 4 over 3 pi r cubed with respect to r.
Is that 4 pi r squared?
You guys agree with Justin? Yes?
Isn't
that
it
the
just
area?
pi r squared?
Pi r squared is the area of a circle. We're talking about a solid sphere now.
Okay.
The skin of the orange. We're not talking about just basically about flattening it. We're talking about the orange. When you peel it, you measure the skin in there. That's 4 pi r squared. Okay. So the electric flux then for a point charge is the following. Phi s of E is equal to 1 over 4 pi epsilon naught times q over r squared times the area of the sphere. You see the advantage of, we actually did not do the integral, we just Googled this stuff in here and we found it. Do you guys see any cancellations in here?
R squared and pi.
R squared gone.
4 pi's.
4 pi is gone. And the flux, as I said before, is just a measure of the strength of the charge divided by epsilon naught. So that is actually the density of the field lines, as we described it. If we agree to draw 1 over epsilon naught per Coulomb, okay? We can draw anything we want, but the result doesn't matter really. But it matches perfectly with this result in here. if we do it this way. So this is the flux of a point charge on a sphere. How about if I don't really have a sphere? I have something else. Let me check on it. Okay. Let me take now the same point charge on any closed surface surrounding it. Surrounding a charge Q. So here is a surface that is completely not actually, this is a surf, no, what should I put it? It's a three-dimensional object. It's like you take your basketball, for example, and you deflate it and you shape it whichever way and you put a charge inside of it. And now you want to find the flux in it. It's not a sphere and it's not an open surface. It's a closed surface. So the flux is still given by that same expression as before. So the flux in this case for this point charge is going to be Q over epsilon naught, 4 pi epsilon naught, I'm sorry, times the integral over that closed surface. That's why I need the circle in here, albeit it's not a sphere, times, in this case, is going to be E. I'm sorry, why did I put the Q in here? Remove, because E is changing. So it's going to be E dotted with dA. Okay, so this expression is put back into E. The reason why I cannot really do that anymore is because this distance now is different than this distance, which is clearly different than this distance. So the electric field changes. So I cannot say, like I said before, when you sum through this area in here, it's the same area, therefore you're in business and so on. It's not as trivial as before. But what I'm going to say is the following. Actually, I can do it two ways. I can argue based on the fact that now the electric field is radial everywhere. So the electric field is still pointing, and this point in here is pointing this way. Okay? But the surface itself, the patch of the surface may be pointing this way. So there is definitely an angle between them. But there are two components to this surface. There is one that is perpendicular, that is going to contribute nothing. And there is one that is radial, that is going to contribute something. And the radial component is proportional to r squared, and the electric field is proportional to 1 over r squared. So if I move around through this surface now, if I move the patch around through the entire shape, not just through this line, by the way, through this entire shape, at some point, r is increasing, the area is increasing, but the 1 over r squared will cancel that increase. And sometimes it's decreasing the area, but the 1 over r squared will increase with decreasing r's. So there will be this match that will cancel them. And the other contribution will be 0 exactly, because it's perpendicular. So always there will be cancellation, instantaneous cancellation between the increase and the decrease. And we're going to recover the same value. So the only thing that matters is the solid angle, which turned out to be 4 pi in this case. That will cancel the other 4 pi, and we're back in business. Another way of looking at it is this way. If I take a sphere now and measure the field density in here, and let's say, for example, I find a certain number, 1 billion of them, for example, or 3 billion, or it doesn't matter how many they're coming. All of these field lines that leave the sphere must also leave the closed surface that is not a sphere. So the measurement in here will be exactly the same as before, and I'm going to get the same result, regardless of the shape of the surface, whether it's a sphere or not. The answer is going to be Q over epsilon naught. Okay. One thing before we go into the next step, before we invoke the superposition principle. If the charge now is outside, here's the charge Q, and I come up with that deflated basketball and put it in here and try to find the flux through it. Now the result is going to be different, because on one side, the electric field is going in and the area is coming out. So this contribution is going to be negative. And that field, when it comes out, is going to come out from the other side, and the area is going to be positive. If I count the field lines, there will be a certain number that come in, and it's exactly the same number of the field lines that come out, and they will cancel each other. So the flux of the electric field over this closed surface that does not enclose the charge is 0. So phi sub E is equal to 0 for charges outside the closed surface. Okay, so we have to make a distinction. Is the charge enclosed or not enclosed? If it's enclosed, include it. If it's not enclosed, ignore it. Here is the step before last. We have a charge Q1. We have a charge Q2. Now we have two charges. And I have an arbitrary surface in here enclosing both of them. What is the flux of these two charges? How am I going to handle it? Because that thing that we've been calculating is for a single point charge. Now, if I have more than a charge, what should I do? Who should I call? There is something that we're going to call to the rescue in here, and it's going to help us solve this thing. We used it already in chapter 21. You guys remember him? Your BFF, your best friend forever.
Coulomb's law.
Coulomb's law actually is a law, but there is a principle I used there when we are dealing with two charges or more. You remember?
Oh, superposition. Yeah.
Superposition. So basically what I'm going to do when I have two charges, I'm going to ignore the first charge and calculate the flux for this charge. It's going to be exactly Q1 over epsilon naught. And then ignore this one as if it's not there. I'm sorry, ignore this one now. And as if it's not there, and just focus on this one, and it's going to be Q2 over epsilon naught. And say, by superposition, the flux now for both charges is going to be just the sum of these two quantities, namely Q1 plus Q2 over epsilon naught. Okay? So if I have a bunch of charges, now I know what to do. Then the flux, which is by definition, by the way, over closed surfaces. Yes, it has to be over closed surface. So this is over closed surface. Of EDA is equal to the sum of the charges enclosed. Because if they are not enclosed, I just argue that they don't contribute, period, end of the story. They don't help whatsoever. When the charge distribution is not discrete like this one, when it's uniform, I have to integrate. I have to sum through all the charges that are enclosed. So if I have a blob of charge in here that has a distribution rho as a function of r, and I want to find the flux over the surface, phi, sub E, then I have to sum through this charge enclosed, through this volume, basically. Actually, through the entire volume where there may be more charges in here. So in this case, I say the flux of the electric field, which is by definition is the flux, in this case, on a closed surface, by the way, of EDA is equal to 1 over epsilon naught, the sum of all the charges inside that volume. This expression doesn't look pretty at all. The volume surrounding or enclosed by that surface. When I say by that surface, I mean specifically this one. Okay? By that surface, I'm referring to that surface, okay? So this is the surface that I'm trying to find the flux through it, S, and I have to sum through the volume that is enclosed. Remember, this is a closed surface. So it's not an open surface. An open surface don't enclose any volume whatsoever, okay? If you take the deflated balloon, for example, and make a cut through it and open it, it cannot contain any volume whatsoever. So this doesn't work on it. It has to be still basically closed for this one to work, so that you have a volume inside to find charges in it so that you can sum them up. So this is in its full glory. Obviously, like I was saying before, we're not going to be using it really in this integral form. We're going to be using it actually so that we don't do the calculation. So how do we use this? Because it looks nasty, doesn't it? It looks far more complicated than we started with. We had triple integral to define the charge, and now to find the electric field, and now all of a sudden we have the other side also has double integral. So this is Gauss's law, by the way. Okay. Do you guys agree that this is not pretty?
Yeah, it seems rather tedious.
Okay, so let's use it now. We're done with the theory. We're done with the hard part. Okay. Let's take a wire, an infinite wire. What I mean by infinite is that its length is much, much bigger than a point where I'm trying to find the electric field. For example, y at a distance from the wire. So if the wire is, for example, length is a meter long, I'm looking, for example, in about 5 centimeters, 10 centimeters from the wire. So 5 centimeters, 10 centimeters is small, infinitely small compared to an infinite wire. What I do in this case, I take a charge Q and sprinkle it on this wire. So there is a distribution of charge in this case, which is Q over L, which is a uniform distribution of charge, uniform distribution. Okay, so I have a charge per unit length, lambda. So lambda is measured actually in Coulomb per meter. How many coulombs did you actually sprinkle on that charge, on that wire? Okay, and I want to find the electric field at distance y from it. So the method in here, I have symmetry because of the two facts. First of all, if I move the wire one way or the other, you wouldn't notice if you close your eyes and I move the wire one way or the other, you wouldn't notice. It's an infinite wire. Take infinity and move it one way or the other, doesn't matter where you put the origin on an infinite wire. So that is one symmetry. The other symmetry also, if I tell you to close your eyes, I can take the wire and move it around because it's the same charge distributed on it. So if I flip the ends of it, you wouldn't notice either. So when you open your eyes, did anything change to the wire? No, it's the same charge. Everything looks the same. It's an infinite wire. Do you guys understand? So there is that symmetry. So we're going to take advantage of that symmetry. So the first step is to identify the symmetry. This is actually cylindrical symmetry. So what I'm going to do in here, I'm going to take a cylinder as a made up shape. So we're going to invent a shape. That is in the step 2, is come up with something called the Gaussian surface, where we're going to actually do this integration. So we're going to come up with a surface, and this surface is a made up surface, not real surface. So we're going to come up with it. First of all, part of it has to go through this point y. So this point y, and I'm going to have an area of radius y exactly. That is the base of the cylinder, and another area in here that is of the same base radius y. And now I need the length for my cylinder. So I'm going to invent a length. It's not there, but I'm going to add it up anyway. Now, all of a sudden, I invented something that was not part of the original problem. This did not exist in the problem. L did not exist in the problem. So this is a made up shape. This is called the Gaussian surface. And it's just a mean for me to solve this problem. So whatever I add to the problem should not appear at the end. So L should not be part of the solution. If I find L at the end, I have a problem. Do you guys understand? So how many surfaces? We have this basis, first of all. This is pi y squared, and this is actually the same area, pi y squared. Okay? And I actually have also, if you take a can and you cut it right around along the length of the cylinder and you open it, it's going to look like this. So this is the lateral surface, actually. The lateral surface. It has a length L, but also it has actually a height of 2 pi times y, which is just the perimeter of the circle, whose radius is y. Okay, so 2 pi y, one side, and L, which is just a fictitious thing, it doesn't exist, I added to the problem. So this is the lateral surface now. This is the surface if I open it up, okay? I'm going to take advantage of the symmetry to make the case for the electric field. Here is the case for it. So that's the next step, is to argue based on symmetry the direction of the electric field and the magnitude of the electric field. So here is my argument for it. I state, as a matter of fact, that the electric field is pointing this way, and it's the same value on the lateral surface everywhere. So it's parallel to the lateral surface. This is what the lateral surface is. The lateral surface magnitude is simply equal to height times length. So it's 2 pi by L. So I will know its exact value, but I know also the direction, and I tell you the direction of the electric field in the same is in the same direction as the area, and the electric field is the same everywhere Y is. You tell me, well, I think you're wrong, and I'm going to make a case why you're wrong. You tell me, first of all, the electric field is pointing this way. Pick any direction, doesn't matter, okay? This is what I think the electric field is. You are wrong, you tell me. I tell you, close your eyes. Once you close your eyes, I take the wire and I flip it around. So if it was pointing this way, it should be pointing now this way. So I just contradict you. So it cannot be pointing this way because for whatever reason you can make up for it pointing this way, I can flip it around for you and it's going to be pointing away this way. So neither of these two cases are good. The only case that is going to stay unchanged under that symmetry is pointing away. So if I move it around and if I tell you it's pointing up, it stays up. You guys understand that because of that transformation? You tell me, okay, I agree with you. The direction is fine. But the magnitude, I think this side is actually less than this side in here. So I tell you, close your eyes. Take the wire and move it now. You tell me actually there was only 5 Newton per Coulomb in here, and there was 10 actually Newton per Coulomb in here. Tell you, hold on 1 second. Move the wire, close your eyes. Move the wire so that the 10 will move in here. And now what you thought was 5 should be 10 according to your argument, okay? Because nothing changed. The wire is still the same under that transformation. So the results should not matter. So the only thing that this will hold true is for the two values to be the same. So that is my argument based on symmetry. So the electric field is the same everywhere on the lateral surface, and it's pointing away, pointing up. Because it's pointing up everywhere, the electric field in here is pointing up, the area is pointing this way, so the flux in here is 0 on the base. And so is 0 on this side too, because of 90 degrees. So the flux on the two bases is 0. And the only flux that's going to stay is the electric field, which is constant, times the area. Constant at least on the Y, as long as you don't change Y, okay? So if that's the case, then this integral in here is going to be 0 plus this area times the electric field, okay? And that is actually not good because we have a problem before us. Let me tell you what the problem is. We have a 0 on this base, plus a 0 on the other base, plus the area, which is just 2 pi YL, times the electric field, which we just argued the same value as long as we are on the same Y, okay? Here is this nasty guy that I thought that it should not appear as a final answer, and it should not. But yet it's showing itself in here, okay? So it better cancel. If it doesn't cancel, I have a problem before me. Now, Gauss's law says that this value of the flux, which we just computed, must be equal to the charge enclosed. The charge enclosed is here only, in this shape that we made it up. There is a lambda distribution per unit length, and I'm just taking L length. So there is a charge which is lambda L. This is the amount of charge that is in here. The other side outside of this shape do not contribute. That is the whole point of it. What contributes is just this one. So on the other side, I have lambda L divided by epsilon naught. And all is well, because first of all, 0 plus 0 cancel, the L and the L cancel. That is exactly what I was hoping to see. This L is not part of the problem. This L is actually a made up thing. So the electric field then is going to be equal to lambda over 2 pi epsilon naught times Y, okay? And that is actually the electric field on a wire so that is running by your house if it has charges sprinkled around it, okay? If we did this calculation, by the way, look at the steps that we did. I mean, we'd had to argue geometry and all of that, but once we did it, step 1, step 2, calculation. So here is the prescription on how to use Gauss's law. First of all, identify the symmetry. Symmetry in the problem. Once you find that, then invent Gaussian surface. Okay. and take advantage of the symmetry now. We did to take advantage of it. Use symmetry to argue for the double integral, for the surface integral, without actually doing it, okay, like we just did, without actually having to place all of those things. And then basically find E, solve for E. Okay. We still have about 4 minutes. Do you guys have a class after this one or not?
No.
Can I borrow 5 more minutes from your time and stop this one around noon?
Yeah, go ahead,
Yeah.
Professor.
Okay, very good. So because I want you, first of all, this is the item of the discussion, really. Today, I want you to really make sure you have an understanding on how to apply Gauss's law, okay? So this is really the item of the discussion. I want you to really be at ease with this one. Here is another case in here. First of all, if we did this calculation using the integral, we would get the same result, but it's going to involve some trig transformations and some basically stuff like that. It's going to require a lot of calculation, but we're going to get the same result too, okay? And we're going to do actually the sphere. The reason why I need to do a sphere is actually because it's needed for one of the problems, okay? So we're going to do a sphere, and actually when Mr. Newton derived his law of the universal gravitational law, he was struggling with that expression, how to argue that the value he needs to put for the denominator in his law for the apple was the radius of the Earth. I mean, he knew it was the radius of the Earth, and that's how he used it actually and found the answers to it. But he had to convince people that his calculation is correct. So he had to actually invent calculus, and in doing so, it took him about 4 years actually to publish after that his work and the book. But the thing is, because he was trying to avoid basically the criticism that he was going to get, that's why he was predicting that. But in doing so, he invented calculus. So this is the stuff that is basically borrowed from the things that he did, including this problem, which is actually similar to what he was facing. So this is the problem. We have a sphere of charge distribution uniform, or rho is uniform. So if you're wondering what rho units for rho is how many charges I distribute per volume. And it's going to be in coulombs per cubic meter. So in other words, rho is going to be, if this is a sphere of radius big R, the volume in this case is going to be, like some of you guys mentioned earlier, 4 pi R cubed. So the rho itself is going to be the charge that you sprinkle on the entire solid sphere. And it's going to be this number, 4 pi R cubed. Okay, so that's rho. The unit for it is clearly coulomb per cubic meter. Okay, and I want to know the electric field for R less than R and for R greater than R. I'm going to use I'm going to use Gauss's law. The reason why I use Gauss's law is because I have spherical symmetry. If I take this sphere and spin it around while you're not looking, you wouldn't notice if it's uniform, if it has this spherical symmetry. One way or the other. So the electric field must be radial, number one, and number two is the same on the same sphere. So as long as I am on the same sphere, the electric field is the same. So doesn't matter. So the Gaussian surface has to be sphere too. That's because of the symmetry of the problem. So if I'm inside in here, the electric field is radial and the surface also is radial, and all is well. Then in this case, the flux of the electric field inside is going to be just the electric field, which is the same on this entire surface, times the surface. And the surface of the sphere, we saw it earlier, it's 4 pi R squared. This must be equal to the charge enclosed only. And the charge enclosed is the charge density times the volume. And the volume of the sphere in this case is the volume inside, not the whole volume, which is 4 over 3 pi R cubed. Cancel the R cubed with the R squared, and do not do any more cancellations, because you can find the electric field from this expression to be rho times 4 over 3 pi over, divided by epsilon naught. Don't forget the epsilon naught. Divided by 4 pi epsilon naught. This times R in here, times R. There is an R left in here, okay? There is an R cubed in here. I'm trying to go fast and at the same time try to rho, I just thought it's q over 4 pi epsilon naught r cubed. So I can sub its value in here, and this will be q times what is it? The 4 pi cancels the 4 pi, the 4 over 3 pi cancels the 4 over 3 pi, and it will be left with an r over 4 pi epsilon naught big R cubed. This is inside. This is this case. For the outside, we're going to take a different Gaussian surface. So we're now at this point where R is bigger than R, okay? So in this case, this Gaussian surface also is going to be a sphere and whose radius is little r, which is bigger than r, and the surface is still, in this case, perpendicular, radial, and the electric field is radial by symmetry. Again, if I turn around the sphere, it's not going to change. So the only thing that retains that is that radial direction. Any other direction that you make an argument for, if I switch it around, it's going to be in the opposite direction. Therefore, by symmetry, the only thing that works in this case is a radial electric field. And it's the same value because it should only be this. Again, if you tell me it's a different value, I rotate it again for you, and the value should shift. Since nothing changed on the sphere because it retains its symmetry, the effect should be the same. Okay. Having said that, then the flux of the electric field then is going to be simply equal to E times the area again. This is this big area, this big whole sphere now of radius little r, which is bigger than big R, is 4 pi r squared still, and the charge enclosed is Q. The whole thing now is enclosed, end of the story. So it's Q over epsilon naught, and the electric field outside is going to be Q over 4 pi epsilon naught times r squared. This looks similar to a point charge outside, but inside is actually grows linear with distance. When r is 0, there is no electric field inside the sphere. And as you start to move around the Earth, and somebody mentioned a black hole earlier, this behavior is actually similar to gravity too. When you are inside the Earth, the gravity in the Earth is 0. And as you drag yourself gradually to the Earth until you reach the surface, the gravitational field starts to, it grows linearly. And then after that, it drops like 1 over distance squared per Coulomb, per Newton's law. Similar in here like this one in Coulomb's law because they are identical in their behavior, okay? I wanted to arrive to this result in here because there's all kinds of interesting cases in there in the homework and probably in the problems that we're going to be discussing when we meet on what is it, Tuesday? So unless you guys want to meet later on, and I guess some of you decided not to, do you guys still want to meet later on to do this stuff or not? Or do you want to leave it until next week? Yes, no? Because the lab is not ready for you guys. I told you that.
You mean meet at the lab time for this stuff today?
Yes. Or do you want to leave it until Tuesday of next week?
I would be fine with meeting. I'm not sure about everyone else though.
I'd like the lab, like personally, everybody has their own opinion, but I feel like lab, maybe we could use it for homework because there's a couple questions that I have regarding mastering chemistry, and then maybe leave the lecture.
Okay. So we'll meet at 5 for this thing, and then we discuss homework problems and things like that. Okay. For some people who want to,
Yeah.
Because the lab is not ready. Okay. In terms of capacitance, we're not there yet. Okay.
I'm also in
anyway,
agreement with that.
Sorry.
Oh, I was just saying, I'm also agreeing with that. The homework's a bit challenging, but yeah, lab would definitely be appreciated.
Okay, so basically the electric field inside is going to be E, what is it? E is going to be QR over 4 pi epsilon naught r cubed. And the outside is going to be just 1 over 4 pi epsilon naught q over r squared. Okay, r squared. Okay. If you want to discuss homework problems, please send them to me ahead of time, okay? Because I need to think through them and make sure that I give you the correct information before I give you some nonsense stuff. Can you, Drake and Byron and Marcella and everybody else who have specific questions or specific problems that we want to discuss them?
Yeah. So should I send them over email? Sorry.
Yeah, send them email, a message through Canvas, okay?
Okay. Yeah. And do I send like a screenshot of it, or should I send the problem specifically?
Just
'Cause I
tell me
don't-
what the problem is, okay? If let's say, for example, you have an issue with the integral or an issue with the getting started with the problem or something.
Right.
I have somebody else actually from another class actually who would want to join us too, and
Okay.
I'll bring them in here too. Okay.
Okay, that sounds cool.
Okay. I'll see you guys around 5 o'clock then today. I'm sorry I took more. I think I took 6 minutes of your time, but we needed to get this lecture out of the way so that we can do applications.
That's fine.
Thank you.
Okay.
I'll see you at lab.
Okay.
Yeah, thank you.
Have a good day.
Thank you,
Professor.
Professor. A wonderful
Okay.
day.
You too. Bye.